It's time to build the main puzzle of this legacy coin, and that's going to be our legacy puzzle. So let's get started with that right now in this video. I'm going to create a new file in my legacy project, and that's going to be called legacy.chialisp. So chialisp file. And to start out, as in every chialisp file, I'm going to use mod, which is basically saying run this, and then we need some arguments to pass in, and do that. Here. Let's just call these inputs. I'll just make some notes for myself while I'm setting this up. Then we'll have some functions, and then we'll have a main function to end it. Okay, the first thing I'm going to add though, before adding anything else, I'm going to use a couple of external libraries in this puzzle, and I'll just type them out right here. You can see them in this include folder. Then I'll talk about them. So include condition codes.clib and include SHA-256 tree1.clvm. Okay, these are widely available. Other people created them, and in case you don't have a copy already, I'm going to put a copy on my GitHub page in the include folder. If you create your own include folder in your project, then these calls should pick them up, no problem. So the first one is condition codes, and this just gives us all of the constants that make up the conditions that you can use in chialisp. And this is all of them. There's not too many really. And it just gives us human readable names instead of having to use these numbers like 51 for create coin. Now we can call it create coin. And it gives them all at once, unlike this password puzzle where I just defined create coin, because I'm going to use several of these for this puzzle. Okay, the other one is SHA-256 tree1, and this is a recursive function, and it's going to give us the tree hash of whatever puzzle we pass in. So that will be quite useful as well in this legacy puzzle. Okay, back to legacy. So the next thing to talk about is inputs. What do we want to include? Well, I've already talked about including an inner puzzle. So we'll do inner puzzle. And the inner solution is something to discuss just a little bit. I guess there's a couple ways to do this, but probably 95%, maybe more of the time, you're going to want to do it the way I'll do it in this puzzle. I'll show you the other way though first, just so you get a feel for it. So you could add an input like arg1, arg2, arg3. And maybe you need to use these arguments in your actual puzzle that you're designing, and then to call the inner puzzle, you would do something like, I won't use the exact right syntax here, but A for execute, inner puzzle, and then you'd pass in arg1, arg2, arg3. Okay, the advantage of this, I guess, is that you're not reusing any sort of arguments. You're just using the arguments that you already have to use anyway in the outer puzzle, which makes the inner solution simple, relatively simple. But there's a big disadvantage of doing it this way, and it's barely even an advantage, because usually, remember, you're not going to be crafting your own inner solution when you want to go spend the coin. Usually some external program is doing that. We're only going to be using this homebrewed, handcrafted inner solution in this training exercise. So it's hardly even an advantage to keep that solution simple. And the disadvantage, of course, is that you are very limited as to what kind of puzzles you can use for your inner puzzle if you do it this way. You have to have these three arguments. And so it essentially has to be the same puzzle, or at least very similar to this puzzle for your inner puzzle. So let's not do it this way. And usually you're not going to want to do it this way. Usually you'll want to just have inner solution. solution, like that. And then when you call it, you'll just call A for execute, inner puzzle, and inner solution, like that. And now your inner solution contains many arguments on its own, but it could contain 0 or more. And it could be any number, it could be any inner puzzle. So now we've made it really generic, and that makes this puzzle much more versatile than it would have been. Okay, so I'll make that call later. Um, the next thing to talk about is currying, and you might be tempted to do curry in the inner puzzle like this. And capital letters just means is a signal that I want to curry this. Okay, you might want to curry this puzzle, but there is a disadvantage to doing that as well. And I really want to thank Quexington for pointing this out. Sometimes this might be the right way to do it, depending on your puzzle. But for our puzzle, let's think about how this legacy coin might be used in the real world. Let's say Alice is the owner of this, quote unquote, owner of this coin. So she creates this puzzle, and her intention then is to put it on the blockchain, and then maybe she wants to do some DeFi on it, some yield farming or something. She wants to make some money on her money and just kind of hold it out there without spending it for, I don't know, let's say 6 months. And her intention then, after 6 months, is to come back, send it to her wallet, reorganize her funds, and then start over again. She has no intention of dying in the next 6 months, and she's not on her deathbed or anything. Maybe she's young and healthy. Who knows? But the default is going to be that Alice is still alive when she spends the money, so she will usually be the one spending it. And the legacy part, as far as passing it on to her heirs, that's only something that's going to happen in the very unfortunate and unlikely case that she happens to die before spending the money, right? So if we curry this inner puzzle, then the entire inner puzzle is just sitting out there on the blockchain. So there's 2 disadvantages to this. One, it's more information than we need. In other words, there's more data sitting there on the blockchain than is necessary to run this code for the most part, as long as Alice stays alive. And you want to limit the amount of data that you put on the blockchain. So that's bad. And also, when Alice goes to spend the money, she'll have to reveal how she was going to give it to her heirs if she had died. So there's a little bit of a privacy issue. Maybe it's not a huge deal, but she might have some sensitive data in that inner puzzle, and maybe she only wants to reveal that once. And so now, if she has to reveal it every single time she spends the coin, then she'll have to keep recreating the inner puzzle, which is quite inconvenient. So for this particular example, it's going to be much better not to curry in the inner puzzle. So we're going to just keep that as lowercase, inner puzzle, inner solution. However, now, of course, this is a problem too, because if the user who is spending the money can just make up their own inner puzzle, then, well, there's no need to have anything built in with heirs. Anyone could just steal Alice's money. So we need to do something else, curry something else in, and that's going to be an inner puzzle hash. So Alice is going to, and by the way, I keep saying Alice as the owner of this coin. Let's just assume she owns the coin from now on, because it's easier to use real names, I think. Okay, so Alice is going to get a tree hash of her inner puzzle, which will be how the money is going to be spent if she dies, and curry that into the puzzle. Now, when Alice goes to spend the money, if she's still alive when she spends it, she can make up her own inner puzzle. I want to give her essentially like root access to this coin. She could just spend it however she wants. She can create her own inner puzzle to send the money to herself or split it up and send it to many people. Everything's completely fine as long as it's Alice who's spending the money. And now she doesn't have to reveal what this hash was. But if anyone else wants to spend the money, they are going to have to send in a puzzle that hashes to the inner puzzle hash. So they are not able to modify the inner puzzle at all. And So you'll be able to see later in the next video when I do the actual spending of the coin, but this creates a huge advantage where Alice essentially has the root access that we want, and everyone else has to abide by a certain set of rules for how this money can be spent. Okay, so the inner puzzle hash gets curried in. There's a couple other things we're going to need to curry here. The big one, of course, is, well, who owns this coin? So we need to make sure that Alice is truly the owner of the coin, so there has to be something sitting in the coin that cannot be modified that indicates ownership, and the best way to do that is with a public key. Okay, so we'll do owner pub key, curried in. The next thing is how to know when Alice has died, and of course we don't have a good way of knowing that, so we're just going to use a time lock function in place of that for this puzzle. So that's going to be wait time, and this is going to be time in seconds until this person's considered dead. And it's a little strange to use seconds because it could be many years, but it's easy to convert 20 years into seconds with just some multiplication. Okay, there's going to be one more input, but I will leave it at this for now. And let's think about the main method. So what do we want to do when the puzzle is first run? Really, when you think about it, there's two separate actions that need to happen here for verifying identity. One is whoever's spending this coin needs to come up and say, I am Alice, or I am Bob, or whoever. And we need to say, is that really the owner? Then we need to verify the identity. So it's kind of like Alice is going up to, if this is in the real world, maybe Alice is going to a nightclub and the bouncer says, hey, who are you? And she says, I'm Alice. And he checks the list and says, yep, okay, you're a VIP. You need to show me some ID first, though. I'm not just going to trust that you're Alice, but based on your word. And if someone else comes up to the bouncer and says, I'm Bob, the bouncer will redirect them to a different line, and they have a different set of rules to get into the club. So how do we do this who are you portion of the puzzle? We need an if statement. So we need if and equal to. So we're going to use that owner pub key. That's the person who actually owns the coin, and whoever is going to spend this coin will then pass in their own pub key for a comparison. So we're going to call that spend pub key, like this. So if the owner pub key is equal to the spend pub key, then, and remember how if statements work, we have the true clause or the then clause, and then this is the false or else clause. So if Alice is, this is Alice's pub key, if Alice's pub key gets passed in, it's like someone coming up to that bouncer and saying, I am Alice. Now the bouncer doesn't just automatically say, okay, cool, you can do whatever you want. The bouncer sends Alice, or says, show me some ID. So what's the show me some ID part? If the two keys match, we're going to need to require a signature. And that is going to verify Alice's identity. So I'm going to call that sign and execute inner. Okay, and I'll create an argument list here later once we figure out what that needs to be. So let's create a function for this verification of identity. So defun inline, and that needs to be sign and execute inner. Again, the argument list we'll do later. Okay, so the first thing is verify that you are who you say you are. So for that, we're going to use an aggregated signature. So that will be a condition, which is part of a list, and I'm going to write ag sig me. So let's look at what does ag sig me do. That's going to be here. This is chialisp's it's hard to say that word, Lisp's documentation. And this is section 2, coin spends and wallets. And if you scroll down, they have a list of all of the potential conditions. And there's 2 for aggregated signatures. One is labeled unsafe and one is labeled me. And if you read through this, you'll see that usually you don't want to use the one that's unsafe, and that's why they've called it that, because it doesn't have this entropy from the coin ID. So if you use it once, then someone will know the signature and could potentially use it later if you ever require the same signature. The way this AgSigMe works, though, is, and we'll see how this exactly works in the next video, but we're going to add the coin ID to the signature. And remember, coins can only ever be spent once, so the coin ID will change every single time that this signature is used. And so therefore you can never reuse the exact same signature, and so this is much safer to use. So you usually want to use this one, which we'll use right now. And we need a pub key and we need a message. So let's go back and add those. So the pub key, okay, we could use either of these because they're identical, right? Let's use the spend pub key. And what should the message be? So when you think about the inner puzzle, I want, again, this is the case where Alice is trying to spend her own money. I want her to be able to create whatever inner puzzle she wants. If she does that, and now the farmer farms the block, and she sees this signature, and the signature is valid, well, or the farmer sees the signature is valid, right? Now the farmer could change the inner puzzle because that has not been curried in, and change the solution. So we want to make sure that doesn't happen. And so the way to do that is by saying SHA-256 tree 1 of inner puzzle. Okay. This will protect against the farmer modifying the inner puzzle. So we're hashing the inner puzzle, and we're including that within the signature itself. So if the farmer does try to modify the inner puzzle at all, even changing just one character, then the signature will not work anymore because it's dependent on the hash of that inner puzzle. All right, so that's a little bit of security. And now we verified Alice's identity. So this is the equivalent of the bouncer checking the ID and then saying, okay, Alice, you're good to go. You can go ahead and do what you want. So she's going to spend the money how she wants to spend it, which is going to be represented by executing that inner puzzle. So A to run, and inner puzzle with inner solution. And these are the ones that the inner puzzle and solution that she made up. Great. So there's one extra thing that I still need to add to this. If you look here, we've created a list and then of conditions where there's only one condition. And this puzzle is going to return also a list of conditions. So we're going to have two separate lists, one that starts and ends here and one that starts and ends here. That's not good because when we go to execute this, chialisp is going to read this first condition and go, okay, the list is done, I'm done. And it won't ever actually execute the next list of conditions because they're together. So we need to combine these two lists into one. And this is more or less just a syntactical thing, but it's really important. And the way to do that is with a C, which will prepend. So, and close parenthesis. So we're going to prepend to this list. So now they're all just one giant list, and they will all get executed. Great. So we've taken care of the case where Alice is trying to spend the money. What about if anyone else comes in and tries to spend it? So that's this case here. What we need to do next is to see if there really is an inner puzzle hash, because I want to allow for the case where there is no hash. And I guess you could call this the YOLO or YOLO in death type of situation where this is where Alice creates this coin, and she just says, look, if I die before I spend this coin, I don't care who spends it. I'm just going to let anyone go and spend it, whoever comes first. So she'll create an empty puzzle hash, and then I want to give the next person who tries to spend it access to whatever inner puzzle and solution they want to send in, because there was no hash. Now, this is probably going to be a very rare case where this is done, but you never know, it might be, so we need to account for it. So we need to check for that inner hash. Check for inner hash. Okay, and actually before I write that method, I'm going to create this argument list just so I don't forget. So what did we need here? We needed spend pub key, and we needed an inner puzzle, and we needed an inner solution. It's really important to get these exactly right, because if you don't have them written correctly in the correct order, it probably still will compile, but it'll give you weird behavior later. So I've just copied these three arguments and I'm going to paste them here. Okay, let's do check inner hash, check for inner hash. Defun, fun, inline, check for inner hash. Okay, do the argument list later. So what do we need to do here? We are going to see if that inner hash exists. And the way to do that is with another if. So if inner puzzle hash. And again, true, false. Okay, the way that if works in chialisp is if there's anything other than an empty list or a null, it will always evaluate to true. So if there's anything there, we'll execute this clause, and if there's nothing at all, we'll execute this clause. But remember, this is not Alice trying to spend the money anymore, so before we do that, there's one really important thing that we need to do, and that is do that time lock feature. So we want to make sure Alice is dead before we execute this this function. So we're going to do assert seconds relative. And assert seconds relative is another one of these conditions that is in this list here. It's down toward the bottom. And where is it? It is right here. We just need a number of seconds, and it essentially just says that this number of seconds must pass after the coin is created before it can be spent, which is exactly what we want, and we're just going to pass in that wait time. Okay, so this verifies that Alice truly is dead. If this has not, if this condition doesn't pass, then whoever's trying to spend this puzzle cannot do it. So then let's say we get to this inner puzzle. Now, if I'll do the false case first. If there is no inner puzzle, again, this is the YOLO example. Alice just lives it up throughout life, and she's very generous. She doesn't care how they spend the money, so we're just going to allow this person to spend the money. So it's the same as this command here. So inner puzzle and inner solution. Great. The next piece of this, we're going to need, if there truly is an inner puzzle hash, we need to make sure that the user, the spender, sent in an inner puzzle that hashes to exactly this hash. So that's the next thing to do. So we're going to do verify inner. And if you remember from this one, there is the same problem is happening here, where we have a list that will end, and then if this gets executed, it'll create another list which won't actually get run the way I've implemented it so far. So I need to do the exact same thing as below and put in a C for prepend and end it here, and I'll just tab these over to make it more readable. Great. So we're prepending the assert seconds relative to make sure Alice is dead, checking the inner puzzle hash. If there's no inner puzzle hash, just execute it. And if there is one, we're going to verify that the inner puzzle is correct. So let's define that function. Defun inline verify inner, and argument list TBD. Okay, so we need another if statement. If, and we need to see if that inner puzzle that was hashed in, the inner puzzle hash, is equal to, and we're going to use that tree hash function again, SHA-256-tree1, to get the tree hash of the inner puzzle that was passed in. Okay, and this will end the if statement. So again, true and false parts here. So we're just comparing the tree hash of this inner puzzle with what was already there. And so if that inner puzzle is not perfectly spelled out by the user who's trying to spend this, which let's say Bob is trying to spend it, then it won't work. It'll fail. So the false statement, all we need to do is raise an exception and say inner puzzle does not match hash. And by the way, this cost me maybe an hour of my time. Once I had, I originally wrote this as doesn't with an apostrophe. That is not good. Don't use apostrophes in these comments. Maybe there's a way to escape it. I haven't tried. So I just will avoid using an apostrophe. Does not. So the last thing that we need to do really is say what happens if these two puzzles do match. Well, great. Now I just want to execute it. Okay. So they've gotten the exact right inner puzzle. Cool. So let's say A, inner puzzle, inner solution. And what arguments did I need to send in here? I needed inner puzzle hash, this one, inner puzzle, and inner solution. And when I called it, I'm going to copy these. When I called verify inner, I pass in those. And I haven't defined these inputs yet either. So what do we need? We need wait time. We need inner puzzle hash, inner puzzle, inner solution. Okay, and we're going to copy those. And where did I call that? Check from inner hash. I called from right here. So I'll paste them here. So hopefully I have everything lined up here. And you can see this is really all we need. We've taken care of every single case where depending on who is trying to spend the money, you'll get vastly different functionality. And depending on Alice, if Alice is alive or dead, that could change things, right? If there's an inner puzzle or not, that could change things. So a lot of stuff is happening here. But you can see this is only a few dozen lines of code that is needed to create all of this functionality. So that's part of why chialisp is really exciting, because it's so powerful to use. Okay, so let's just make sure that this puzzle is complete, that I didn't screw anything up. So I'm going to do cdv clsp build and that legacy clsp. And it will compile. This will take a few seconds. Does it come back? Yes, okay, compilation finished. So this puzzle is now complete, and next we're going to start to create the transactions, and we're going to put coins on the blockchain and actually start spending this. So that's exciting how this is going to all come together, and I'll get to that in the next video. So see you then.